Hello, welcome back to Learn Physics. In today's topic, we are continuing with our electromagnetic induction. Electromagnetic induction, in last class also we learned about Lenz's law and all, and today we are continuing with our eddy current. So next topic is eddy current. So what is meant by this eddy current? Eddy current is the current induced in the bulk pieces of conductor when magnetic flux linked with the conductor changes. So we know that magnetic flux linked with the conductor changes and EMF is induced in it, isn't it? Because of that current developed is called a induced current. So here, if that process is happening in bulk pieces, okay, the current induced in the conductor, which is a bulk piece of conductor, when magnetic flux linked with the conductor changes. So what is this eddy current? Magnetic flux linked with the in a bulk piece of conductor changes, a current is inducing. That current is called as eddy current. Okay, what does this mean by this eddy? Eddy means loops of current, that is a whirlpool, like that it is forming. Okay, it is forming in a continuous loop of current, that is the current will be forming like this as eddies. It will be forming as eddies or whirlpool, like that it will be forming, that is called as eddy current. Okay, so what is this use of this eddy current and how this eddy currents are producing? If we are considering, see, a magnetic in between a magnetic poles, we are placing a plate of conductor. Okay, so that is a magnet which is we are placing a plate. Okay, what will happen? You see, magnetic flux is passing through it, passing through this plate. Okay, if there is no magnetic fields are not there. Okay, if we are not applying any magnetic field and we are oscillating this plate. Okay, this plate is getting oscillated and we are applying magnetic field. What will happen that time? See, it will be oscillating over there. This magnetic plate will be oscillating in the magnet but there is no magnetic field. Okay, simply it will oscillate for a long time. When we are giving magnetic field, if we are applying the magnetic field, what will happen? This oscillation won't for long time. This oscillations won't be there for a long time. It will come back to the equilibrium position fast. What is the reason for this? See, it is forming as eddies of current when magnetic flux linked with the circuit changes. Magnetic flux changes. That time only what is happening? Current is inducing, isn't it? Current is inducing in the circuit. Current is inducing in the circuit. So that current is called a eddy current. So here when it is oscillating, that current is inducing in that circuit. So and what will happen? This current is inducing in the circuit and the direction of the current will be opposing which produces it. Opposing what? Opposing the change in flux. So that will be resulting in the damping of this, or this will be coming almost to the rest position first because of the formation of this eddy current. So this eddy current will be helping the oscillation to stop. Okay, so this eddy current, so you understood what is happening here in the eddy current. So when we are taking a plate of conductor and which is present in a magnetic field, and while we are changing the magnetic field, see, if it is a permanent magnet, we can't change the magnetic field, isn't it? So if we are using an electromagnet, this electromagnet will be helping it to stop. Okay, this electromagnet will be changing the magnetic flux. When the magnetic flux are changing, what will happen? The current will be inducing in the circuit. So the induced current will be opposing the direction of the change in flux. So what is helping it to change the flux? The oscillation. Oscillations are helping to change the flux of in the conductor, isn't it? So it will be helping it to stop. Okay, so eddy current will be opposing the oscillation, so it is helping to damping. That is called as electromagnetic damping. Okay, it is coming, the oscillations will be coming to the rest position faster. So, and it is this is one of the experiments, and the other one is jumping disc. Jumping disc, if you would have heard about the jumping disc. See, if I am taking a solenoid and current is inducing and a key is here. So if I am collecting it to the, and a disc is kept over here, what will happen when current is passing through the coil? Suppose this is the south pole, and when it is current is passing through the coil, what will happen when I am pressing that? So magnetic flux linked with the circuit also changes. If it is changing, what will happen? An EMF will be induced in the coil, and here also, if this is the south side, and the downside of the disc also will be getting a south polarity, isn't it? So it will be getting repel. Repel means it will be jumping from that position. So after that, what will happen? Because of gravity, it will come down, but it will be jumping to that position. So this is jumping disc. That also due to eddy current, because the magnetic flux linked with the circuit is changing. So here it is here we saw it as the oscillation is decreasing. So as area increasing, what will happen? The electromagnetic damping also will be more. But if we are reducing the area, next here itself, if I am making slots over here, if I am making slots over here, what will happen? Then it will be oscillating for more time. Some more time it will oscillate, because area is decreasing. So magnetic flux linked with the circuit changes also. It is the change also will be decreasing. So it will be oscillating for little bit more time. That means here and all, induced current is depending on area. So the magnetic flux linked or magnetic moment also will be depending on the area of the plate. Okay, so understood, as the area increases, magnetic moment also increases. That is damping also, it will be coming to the, as area increases, oscillation will stop faster. As area decreases, what will happen? Area also will be, this oscillation also will be continuing for little bit more time. Okay, so you understood what is this electromagnetic damping. Okay, this electromagnetic damping or this formation of eddy current has many applications. The first one is in the case of galvanometer. So application. First one is in the case of galvanometer. Galvanometer, see, while we are connecting the galvanometer to the circuit, you can see that that galvanometer needle will be deflecting. It won't be coming to stop position fast. It will be deflecting. It will take some time to we should wait for some time to take the result, to come to the exact position. The needle should be in the proper way after a little bit of time. What is the reason for that? Because of electromagnetic damping or formation of eddy current, what will happen? The oscillations will be like this. That oscillations can't come to the rest position fast. It will take some time to come to the main position. So here, instead of this one, here we are using a non-magnetic coil over there. What will happen? Then eddy current will be forming over there, and that eddy current will help the galvanometer to come back to the rest position faster. So it will, the oscillation will become less. So it will come to the rest position fast, and it will be easy for us to take the reading. Okay, so here that also we should use a non-magnetic coil over there. So then because of eddy current, it will come back to the rest position fast. Okay, so that is one of the applications. So second one is, see, in power meters, the current reader, the meters where the current is reading, there also we kept one disc, metallic disc is there. When alternating current pass through the circuit, magnetic flux linked with the alternating current is like a changing current, isn't it? So it is magnetic flux linked with the circuit changes. So because of that, eddy current will be forming. Eddy current will be helping that oscillation to stop. Okay, so understood this here. And next one is in magnetic trains. in magnetic trains, magnetic brakes will be applied. What is the how it will be applied in magnetic trains? See, trains which are which are using the electric trains, that is electromagnetic electric trains. In electric trains and all, the just above the rails they will be keeping some strong electromagnet. So whenever it is required, that electromagnet they will make it active. That means electricity it will pass, and they will pass electricity through that electromagnet. So what will happen? It is converting to a magnet. At that time what will happen? Yes, magnetic flux linked with the circuit changes and electromagnetic damping will happen. That electromagnetic current will be forming, that will be helping the electromagnetic damping, and it will be helping the train to stop smoothly. Okay, that is another application of this eddy current and her electromagnetic damping. Okay, clear what is meant by eddy current and how it is producing and its application also. Clear for you? Next is self-induction. So what is meant by self-induction? It is the property of a coil by virtue of which it opposes any change in the current by inducing an EMF inside it. Okay, it won't allow to change the current inside it. How it will be stopping that? It will be stopping it by the help of this EMF induced by inducing an EMF in it. Okay, so it is the property of a coil by virtue of which it opposes the change in current flowing through it by inducing an EMF in it. Okay, clear? So if this is the coil and current is flowing through the coil, okay, current is flowing through the coil in this direction. So what will happen? And if we are trying to increase the current, see, I am using a rheostat and I am trying to increase the current. While I am trying to increase the current, what will happen? An EMF will be developing in it to oppose the increase. Okay, so suppose if I am trying to decrease the current, so EMF will be here if I am trying to increase. If I am trying to increase the current, EMF will be developing in the opposite direction. If I am trying to decrease the current, what will happen? This EMF will be producing in this direction to increase, to oppose the decrease. Okay, so and EMF will be helping it to oppose the decrease. So this is what happening in the case of self-induction. Okay, it is the property of the coil by virtue of which it opposes this increase or decrease, opposes the change in strength of current by producing or by inducing an EMF in it. Okay, so the flux linked with the circuit, magnetic flux linked with the circuit is directly proportional to the current flowing through it. That is, to change the proportionality sign, we are multiplying with a constant called L. This is called a self-inductance. Self-inductance. So how we can define that self-inductance or coefficient of self-induction, like that also we can say coefficient of self-induction. How we can define this coefficient of self-induction? See, if I equals 1 ampere, then flux linked with the circuit will be the coefficient of self-induction. So the coefficient of self-induction is equal to the flux linked with the circuit when 1 ampere current flows through it. Okay, so this is, see, but we know EMF induced is equal to minus d phi by dt. So instead of phi, we can substitute it as L into I. So it is equal to minus L into di by dt, isn't it? So EMF induced is equal to self-inductance, coefficient of self-induction, if the rate of change of current is 1 ampere per second. Okay, in that way also we can define the coefficient of self-induction. Okay, next we are going to find out what will be the dimension of self-inductance. Okay, L. What will be the dimension of L? Okay, so dimension of self-inductance, how we can find out? So now we got it as EMF is equal to minus L into di by dt. Like that we got, isn't it? So here L, what is L? E into dt by di. What is E? EMF, how we can find out? Work done per unit charge into dt by di. Okay, work done means force into displacement. Q means what is the dimension of Q? I is equal to Q by T. So I into T. dt by di. So dt and dt will get time and time will get cancelled. So the dimension of L is equal to force. What is the dimension of force? ml t to the power minus 2 into S, that is L, divided by I into I, that is A square. So we will get it as ml square t to the power minus 2 a to the power 2. This is the dimension of self-inductance. So this is the dimension of self-inductance. So what will be the unit of the self-inductance? Unit of self-inductance is Henry. So how we can define this Henry? See, as usual in the previous lessons and all, how we learned about the definition of a unit, in the same way we will consider E is equal to L into di by dt. Okay, so minus L into di by dt, that is when EMF is 1 volt and di by dt is 1 ampere per second, then L is equal to 1 Henry. That is self-inductance or coefficient of self-induction is equal to 1 Henry when 1 ampere of current is passing through the conductor for 1 second, then the EMF developed is 1 volt. Okay, if an EMF of 1 volt is developing in the circuit because of 1 ampere per second current, then the inductance or self-inductance or coefficient of self-induction is equal to 1 Henry. Okay, so this is how we will be defining Henry. Clear? So next we are going to find out what will be the self-inductance of a solenoid. Okay. Self-inductance of solenoid. So we know the magnetic field inside a solenoid. What is the magnetic field inside a solenoid? Mu 0 Ni by L, where L is the length of the solenoid, N is the number of turns in the solenoid, I is the current flowing through it. Okay, so what will be the flux linked with the circuit? Magnetic flux. How we can find out? Magnetic field into area, isn't it? B dot A, isn't it? So B into A. B is mu 0 Ni by A, Ni by L into A. This is the flux. Okay, in 1 turn. This is the magnetic flux linked with the circuit in 1 turn. If there are n number of turns, so what will be the magnetic flux in n turns? This is for 1 turn. Now it is mu 0 Ni by L into A into N. This will be the magnetic flux linked for n turns. This is the magnetic flux linked with the circuit in 1 turn. This is the magnetic flux linked with the circuit in n turns. So it will be mu 0 n square Ia divided by L. Okay, but phi, what is the value of phi? Phi is equal to L into I. That one we already got it, isn't it? Phi is proportional to I, therefore phi is equal to L into I. Here, while we are comparing these two equations, left hand sides are equal, so we can equate the right hand sides. So that is mu 0 n square Ia by L is equal to L into I. Now, here I and I are same both the sides, so we are cancelling it. We will get it as mu 0 n square A by L. This is the self-inductance of a solenoid. So instead of this is permeability of free space. If I am considering a permeability in any one of the medium, and mu is equal to mu 0 into mu r. So instead of mu 0, we can substitute it as mu 0 into mu r into n square A by L. This is the self-inductance of a solenoid. Clear this? Very easy. Magnetic field of the solenoid, we already learned that, isn't it? So flux B into A and N turns, equating, we will get the answer. Okay. So next we are going to find out the electromagnetic potential energy. How we can find out the electromagnetic potential energy? Here in the self-induced EMF we will call otherwise as back EMF. What is the reason? Because it is opposing the current in the change in current, isn't it? Because of that we will call it as back EMF. So to oppose something we should do some work, isn't it? So that work done to oppose this current, that work done will be stored as magnetic potential energy. So to calculate the magnetic potential energy, we should find out the work done. How we can find out the work done? See here, EMF we already learned it as work done divided by charge, isn't it? So work done will be equal to EMF into charge. But we know, see, I is equal to dq by dt. So q equals I into t. So I into t into E, that is work done. So work done divided by time, that is equal to I into E. Okay, but E already we got it as L into E is equal to L into di by dt, isn't it? So here we can write it as I into L into di by dt. Okay, so if time is L into di by dt, this is for a small interval of time dt, isn't it? So if here we can consider it as, if we are considering everything as a small interval of time dt, then we can write it as w by dt is equal to I into L into di by dt. So this dt and dt will get cancelled. So we can find out the total work done as. So dw is small work done for a small interval of time dt. So we can write it as dw by dt is equal to I into L into di by dt. So we got it as L into I into di. That is dw. How we can find out the work done? Integral 0 to I L I di. What is I di? L into I square by 2. That is work done, we are getting it as half L I square. Okay, so this one, are you remembering about half mv square kinetic energy? That resemblance is there here, half L I square. And the self-inductance we are considered it as, it is the property of inertia. Okay, so or we can say it is the electromagnetic analog of mass. It is the electromagnetic analog of mass. Okay, so here how we are coming to the finding out the work done? EMF is equal to work done by charge. Therefore, work done equals EMF into charge. So W equals charge equals dq equals I into dt. Okay, so here for a small interval of time dw, while we are calculating, dw by dt is equal to I into E. I into, instead of E we can write it as L into di by dt. So we will get it as L into I into di, that is work done will be equal to half Li square. This will be stored as gravitational potential energy. Okay, sorry, magnetic potential energy. Okay, this is the magnetic potential energy, and that self-induced EMF is called as back EMF also. That also you should remember. That's why that negative sign is coming over here, because of that back EMF. Okay, so understood. And self-inductance is considered as it is the role of inertia in our mechanics. Okay, it is the magnetic analog of mass. Okay, understood. Today's topics are very important topics. Eddy current also very important, self-inductance also very important. In next video we will be taking the mutual inductance and AC generator. Okay, I hope all of you understood all those things, and if you like the channel, please don't forget to subscribe. Thank you for watching. Bye.